Hi, this is Kirti. I'm going to present the topic self-organizing queue-based clustering for the class pattern recognition and intelligence. So what is clustering? The technique of clustering is used to segregate the objects in different groups in order for similar objects to be combined into one group and non-similar ones to form a separate group. By comparing various objects, we can actually cluster them very easily. It aggregates the comparable objects in the same clusters by maximizing the inner cluster differences and intra-cluster similarity. Clustering can also be used in different scientific research areas to find out meaningful results. It mainly has its applications in machine learning, pattern recognition, and data mining. What is cluster model and clustering algorithms? There are many clustering algorithms based on the data objects on which they have to be applied. Different cluster models may vary significantly in their properties. The different cluster models are connectivity models, centroid models, distribution models, density models, subspace models, group models, and graph-based models. All of these models have been discussed in the class by Dr. Wu. The different types of clustering algorithms are hierarchical clustering, distribution-based clustering, density-based clustering, and spectral clustering. What we are most interested in right now is spectral clustering. Self-organizing queue. Graph clustering, also known as SOQ, that is self-organizing queue clustering, is the self-organizing ability of fictitious nodes in order to group similar kind of objects into a same cluster. What is self-organizing? This technique works around placing the existing nodes into queues where each queue belongs to a separate cluster. All the nodes having similar properties are aggregated into the same cluster, and this is enabled by the self-organizing abilities of every queue. The results obtained from these methods have been proven better and exact as compared to other existing methods like K-mean algorithm, N-cut methods, NJW spectral methods. So this clustering method is same as how we humans differentiate the objects. So if we take this example of a working SOQ, so we have two classes of objects. One is represented by a circle and another is represented by a cross. So if we want to segregate the class into two different types, so what happens is that we take a central object in the queue, and at a time only one object can move. So the two groups have only the objects from each separate class in them. So if we take, for example, the circle, it looks around, it sees to the left and to the right. If there are more number of circles on the left than on the right, it moves to the head of the tail, that is to the right. And in case there are more number of crosses to the right than to the left, it moves to the tail. And it continues to do like this unless it reaches a point where there is no more change. So in this case, we see that when the time reaches t is equal to 20, the clustering stops. That is, the clustering is done and the objects stop moving. SOQ clustering algorithm. What are the various variables that we used in this clustering algorithm? It is current queue that points to the current queue. The current person represents the node, that is the current person in the node under consideration, and next queue is the one where it points to go to the next queue. The similarity matrix used in this case is of the order n by n, where every wij represents the similarity between the nodes I and j. This similarity matrix is converted to a similarity matrix by adding a negative sign to it. All kinds of real numbers can be taken into consideration. What are the various steps of self-organizing queue-based clusters? The input to this algorithm is a set number of nodes, that are n nodes, and the similarity matrix W. We begin with initializing it first. N number of nodes are divided into k queues. Then a queue is assigned to the current queue and a flag is set to be 1. While the flag is set, we decide who, how, where, and when the next queue will take place. So this is used to choose who is the next current person in the current queue. How? It helps in determining which queue is going to be marked as the next queue so that the current person can join it. Where this step determines the placement of the current person in the next queue. The next queue is assigned to the current queue, and the when part determines the end of the loop and sets the flag back to 0. Unless the flag is set to 1, the loop continues, and when it's set to 0, it stops. The end while loops. When the while loop ends, the program stops. The output is that we obtain k clusters or queues. There are 3 types of SOQs that we've used in this paper. The first one is the simple self-organizing queue. It is sequential, self-organizing, and the similarity matrix can be asymmetric, and the entries in the similarity matrix can take on any real values, even the negative ones. The only problem in this algorithm is that when the current person moves to the next queue, the current queue becomes empty. To overcome this problem, we came up with the idea of one cluster being empty SOQ, that is CESOQ. It is almost similar to first algorithm, except that upon partitioning the clusters, we find a pair of clusters having the minimum crosstalk density. I'll show you the formula for crosstalk density later in the slides. One of the 2 clusters with the minimum crosstalk density then replaces its original queue, and the other cluster replaces the empty queue. So the limitation of the current queue being empty is overcome. But this algorithm also has a fault that within cluster crosstalk may be smaller than the crosstalk between the clusters. So this problem was overcome in the third type of algorithm, that is merge split SOQ. It is similar to CESOQ, but it has 2 additional steps. In this algorithm, we compare the within cluster talk of the cluster with the crosstalk between the clusters and decide which one the new queue is going to be. This helps in eliminating all the errors encountered in the previous 2 algorithms. So how have we implemented this algorithm in the project? So the code I've taken up is actually the one provided by Dr. Wu on his website. So this code has a function DCSOQ which acts as the main function and is defined in the file main.m. The first step is initialization, which is responsible for dividing the data randomly into clusters by using the function initialize queues. I'll show you all the codes when I run the program towards the end. So this function initialize queues returns 3 variables: the queues, the labels of the current person, and the number of current queues. Now we go through all the members of the initial queue and put them in the correct queue as desired with the help of the clustering thing we discussed in the first algorithm. This is done with the help of self-organizing function. This is a function defined again in the MATLAB file, self-organizing queue with initial queues. So in this step, we basically calculate the appropriate queue for each member with the help of the following formula. When this function runs its course, the difference between the queues is determined by using the crosstalk density formula that I said that I would show you later in the slide. So this is the formula by which we calculate the crosstalk density. In the same way, we calculate the crosstalk density within the cluster. Now therefore, we have 2 values, row between, that is between the cluster, and row within, that is amongst the clusters. The conditions that follow now determine the course of action so as to what will be marked as the next queue and what to merge. If the flag is set to be 0, the loop is terminated. If not, the loop continues and returns the clusters. The function reorganizing queues has 2 other conditions. We merge the clusters depending upon the crosstalk density value here and decide what the next queue is. In the function DCSOQ of the initial queue, if the initial queue is equal to queues, then the initial queue is updated. So main.m basically compares the ground truth, that is the actual number of clusters, with the clusters that we have obtained so as to see that how correct our results are. So this is where the experimental results have been shown. We test the performance of MSSOQ with synthetic and real-world data. and compare it with the results obtained from other algorithms like k-mean, spectral clustering, NGW, and NCUT algorithm. The synthetic data that we have used for this case is a collection of 2D Gaussian distribution having a standard deviation of 0.05 and mean of minus 0.03, 0, 0, 0.3, 0, and 0.6, 0, with every 2D Gaussian distribution corresponding to only one cluster. For the real-world data, we have considered a set of data where the handwritten digits were scanned and uploaded. These two are basically two different digits, 3 and 9. So after doing this, a similarity matrix is generated for spectral clustering algorithms and is represented by this formula. Now these are the results that have been obtained. This ground truth similarity matrix is the one that is like the one with which we compare our results. This is the similarity matrix before the random permutation, and this is the similarity matrix after the random permutation. So our program has the option that we can either randomly permutate it or we can just take set defined values. So figure A shows the similarity matrix before the random permutation. The darker the entry, the greater is the similarity, and figure B is a depiction of the similarity matrix of sample points with randomly permuted entries. These figures are obtained after the clustering has been done. This is the outcome that has been obtained after applying NCUT algorithm, and this is the outcome of MSSOQ. We can clearly see that this has better clustering. So what this also, after remapping it, we see that we obtain the same cluster as we provided to it, like this data. So it shows that this MSSOQ has no error. Each similarity matrix shown in figure D and E is permuted according to the clustering results. Upon remapping, it was observed that the clustering was same as in the original case, showing that MSSOQ is capable of producing zero clustering error. When we run the MATLAB code, this is what is generated in the command window. It actually shows that the Q results before the random permuted are this, and when they were compared with the ground truth results, they were this. And the confusion matrix for the ground truth is shown, it is symmetric, and the confusion matrix after matching is also same. And there are no errors. We see that SOQ has been completed perfectly. If we compare the performance of MSSOQ with other algorithms, we see for even for clustering for synthetic data and real world data, the clustering performance of MSSOQ is greater and there is zero error clustering. And but the only problem is that the time complexity for SOQ is higher than other algorithms like NCUT, NGW. But even despite this fact, we still prefer to use MSSOQ because it is much better in performance as compared to other algorithms. Now I would like to show you the code for this program. So this is the main.m file I was talking about. It has this part is the random we generate the random sequence. If I comment this one out, I can use a no random sequence, it means it uses the similar results every time. And this is the self-organizing queue within initial queues, which updates if the initial queue is not same as the provided queue. Then this function load data, it can either take the data that we provide, or if we want to provide a different data set, we can actually load another .mat file here and it will take those values. Apart from this, this is the DCSOQ function. That is one of the very important functions that describes how and when it is initialized. Now I'll run the main.m file and show you the results that we obtain. So this is the clustering result, the MSSOQ that we actually require. This is the randomly permuted similarity matrix, that was the input. This is also the input, that is the ground truth that we use to compare our values to, and this is the input data that we gave, the 2D Gaussian data. In the end, I would like to thank Dr. Wu for being there and for helping me learn a lot in this class. And I would also like to thank our TA for always being there to solve our doubts. These are the references that I refer to. First was the paper by Dr. Wu, and then I refer to the class notes, and there was this another comparison of different spectral clustering techniques that I used. Thank you so much.